Begin YouTube video. Okay, so today we're talking about t-tests. Indeed, there used to be a person in our department, a student, who we called t-test because he would constantly ask the question, would that be a t-test? So that became his nickname. It did. Actually, he might have even helped you guys out in 2126 sometimes. Mike Storazak, do you guys know him? Yeah, t-test, that was his nickname. Paul and I called him t-test. Okay. All right, so today, like I said, t-test, something that we all know about. Oh, look, I changed it. It looks nicer now. Remember to find the probability of a given value of a variable. This is what we did last time with the probability mass function. So any variable that's normally distributed, you'd use our old friend, the z-score. You look it up in a table. So you get x minus mu, divide by sigma. In other words, you're getting standard deviation units. You divide by, so x minus mu, difference from the mean, divide by standard deviation. You get a z-score, you look it up in a table. And as old people say, and then Bob's your uncle. I don't know what that expression means. It's something people say. And then Bob's your uncle. No, I have an Uncle Bob.
I have an Uncle Bob.
Really? So, and then we go see her Uncle Bob. And he has his end table, and everything's great. You're a good group. I enjoy the laughter and the enjoyment. By the way, all you guys, I don't know if you know this, this is picking up everything you're saying, and it goes on YouTube as well.
Oh.
It's a pretty good microphone for that. So we've done that, you've done that, no one ever does it in real life, because we ever know real standard deviations, but it's a start. We do this for a reason. We start you here for a reason. And that's being sarcastic. That isn't that interesting. Is it ever coming up funny? It's probably because I'm running 800 different apps right now. We're usually dealing with means, not individual values, right? We're not dealing with individual values. We don't care if, except under very specific circumstances, one of them perhaps being, I don't know, your GRE score when you apply to grad school. You want to know your actual percentile. Sure. That's about the only one I can think of. Or, maybe when you have a little baby and you take him in and they say, he's in the 63rd percentile for height. No one calls baby height, they say length. Because they don't say that.
What?
And he's in the 53rd percentile for weight. Everything's fine. With my son, he's in the 98th percentile of everything. He's going to be a giant. That's really a Z table. That's what the doctors looked up. The doctors don't know that because they forgot all their stats. Because they're sitting around bathing in their money. They sleep on beds of money most of these. Okay. We care about means, right? Is this group different from this group on average? So instead of knowing about the distribution of x, we want to know about the distribution of x bar. And I talked to you about this the other day, about sampling distributions and the sampling distribution of the mean, which is just a distribution of all of the values the mean can take. And, their associated probabilities. Okay, questions so far? Yeah, you know this, right? Now this, you are to memorize. Now, again, it's an open book test, usually so who cares, but this is something you should know. You should take this to heart. You should say this to yourself as you go to sleep each night. It should become something you just say. Given a population with a mean mu and a variance sigma squared, the sampling distribution of the mean will have a mean of mu sub x bar equals mu. And a variance of sigma squared divided by n. As n increases, this distribution approaches normal no matter what the shape of the parent population distribution. There's a reason I bolded that. That's a really neat and important thing. We always get a normal distribution for sampling distributions of the mean. We always do. And I know a lot of times you hear people say, well, once you get to about 30, it's normal. Once you get to about an n of about 5, it's basically normal. Okay. 30, it's almost indistinguishable. But by about an n of about 5, you're going to get basically a normal distribution. It's pretty amazing. We talked about that the other day, about rolling a die or flipping a coin. I imagine no one here actually rolled a die 10 times and got the mean score and did it 1,000 times and plotted it. Anyone? No? Okay.
Yeah.
But you would get a normal.
Does this like do in there?
Fair enough. Questions? You've seen this before. This has a proof that we're not going to go into because I can't remember it, and it wouldn't help anybody. As I've said before, there is a proof, and if you want to see it, you can come out so I can show you, or we can pretend you're all Catholic and I put Dave the First and I was completely fallible. I'm that new young pope on HBO. It's me and Jude Law. Seen that? Is that the show? It looks okay. I watched the first half of the first episode. Well, no, whole first episode. It's a little weird. Okay. You know this. This is something that was told to you in 2126 that was drilled into you. No problem. Okay. Any questions before I move the slide?
Not yet.
Not yet?
Please.
Okay. Don't move it? Okay.
Yeah.
Well, maybe I'll perhaps perform a song. All it's saying is that if the mean of the variable is 10, the mean you will get, which is a weird thing to think of, the mean of the means would also be 10. And if the variance is, 100, and you've collected 10 pieces of data, 100 divided by 10, so it's n of 10, you're going to get a variance of 10 for the sampling distribution of the mean. Okay. Make sense? You good? Okay. We're moving. This is a very powerful thing when you think about it. It's one of these really neat things because when you sort of put your head around this, there's a lot of power for inferential power in this. The population distribution shape does not matter. We know the shape of the sampling distribution. We don't have to know anything about the population distribution shape. We can make guesses. We don't have to make guesses. It doesn't matter because no matter what, it's going to be normal. That's really cool, actually. That's a really weird property of the universe. It's very neat. Random sampling matters. This assumes a random sample. Now, it doesn't matter nearly as much as you probably have been told it does. But it matters some. But it doesn't matter a great deal. So there's the estimate of the mean, that's mu being the mean of sampling distribution, mu sub x bar. It's very resistant to violations of that assumption. Okay? So that estimator has a lot of resistance. It's a technical term. So it can deal with that violations of that assumption very well. So we could do this. I could do a completely non-random. I'm going to do a random sample. I just use like alphabetical order and do heights in our room and do it like 20 times, and I get a normal distribution, even though it's not random. I know I would. And put money down. I bet you a week's pay. Yeah, sure, 2 weeks. You get a couple of cases of beer with that. I'm actually paid okay. I'm almost paid what I'm worth now. Not quite. No, yeah, not quite there. Another 30 grand and I'm probably paid what I'm worth. So to find out the probability of some mean, because that's what we care about, we just use our old friend. Hello, old friend. Z-score, how are you? Because that says, basically, it's going to be normal, so we can use Z distribution. We know what the mean is. The probability, we know what the mean of the sampling distribution is. It's going to be the same as mu. And we can calculate what the variance is, because it's going to be sigma squared over n. So we just divide that, the square root of that quantity. We get sigma over root n, and we're in business. Okay? Questions so far? Yeah, please.
Could you present this to us with an example?
Yeah, sure. So, wait a second. I think the next thing's an example. Yes, I can. In fact, I prepared a slide that does that. Just wait a second. Other questions? Good question. Oh, wait a second. I think that was. Anything else? Okay. So let's say I do it a second. We'll get there. But we can think of this right here. So what happens for our z is it's still the thing we're interested in, that's x, minus the mu, minus the mean, divided by the variance, or the sort of standard deviation. But now it's going to be x bar, because we're interested in means. It's still minus mu. Technically, that's mu sub x bar, because that's the mean of the sampling distribution. But we know that that's just that. And we know the expected value of this is this, sigma over root n. Your example's coming up next. So it's funny, when a lot of times in stats, when you first learn it, it's presented that this is a different formula. This is the Z formula for means, and it actually isn't a different formula. We've subbed in. That's all we've done. Right? We want to know about x bar, not x. We know about mu. It's really mu sub x. And we know that the standard deviation is sigma over root n now, because it's a sampling distribution. It's a mean. So it's actually not a different distribution at all. The different formula, I'm sorry. Or distribution. Okay. So that's how we got here. Now an example. Let's say 25 subjects are given an IQ improvement course, which they're wasting their time. They are wasting their time and their money. And we test their IQs after this course, after we've stolen their money. And they end up with a mean of 110. Okay. IQ improvement course. Their IQs are tested after they take this course. They have an average IQ of 110. We have randomly selected these people from the world. In a world where people are randomly selected for IQ tests, one man has the courage to love. I love the In a World guy. It's one of the greatest guys ever. He died recently, right? I think the In a World guy died.
It's one guy.
In a world where the In a World guy died.
That was like a computer. I always thought that was like a computer.
No,
like,
that's
not
a guy.
just one guy.
That's one guy. Yeah. It's the In a World guy. He's got a union. He's the only member. So, we know that IQ in the population is a mean of 100. That's the way IQ tests are designed. We know that IQ, the reason we use IQ all the time is we know the variance and the standard deviation. Variance is 225. Standard deviation, therefore, is 15. Okay? So the nice thing about that is now we can use this information to answer the question, did our IQ improvement course work? Okay. Did it work? Well, the way to solve that, the way to figure that out is to put it to find out how likely it is in the population, if we randomly selected 25 people to get a mean IQ of 110. How likely is that to happen? That's really the question we're asking. Our HO, if you want, is that mu equals 100, and our HA is that mu is not equal to 100. Or we could make it directional and say mu is greater than 100. We could hope that the IQ improvement course wouldn't drop people's IQs. The IQ improvement course just involves me punching you in the face. That might drop your IQ. It just involves a series of minor amounts of brain damage. Where do I come up with that? You know, what you think? I say everything that comes to mind. I edit out a lot. There's a lot of really offensive stuff out of my brain that I don't say. And a lot of really offensive stuff I do say. But still, okay, so this is what we do. Here we are. Z equals x bar minus b over sigma divided by root n. So 110 is the mean we're interested in to see how likely it is. We know what the mean in the population is. It's 100. We divide by 15, that's sigma, divided by the square root of 25. It's amazing how I decided to use something where I didn't have to use a calculator to figure out the square root. Square root of 25 is 5. So then we go, it's 10 over 15 divided by 5, or 10 over 3, which is 3.33, which actually, it's exceedingly unlikely to get a z-score of 3.33 if the population has a mean of 100 and a standard deviation of 15. In fact, it's so unlikely, I bet that entry is not even in your textbook, in the z-table. Most of them only go up to 3. I looked it up. The probability of getting a z greater than 3.33 is less than 0.00043. I didn't look it up. I put it in my calculator. My calculator does z tests. That I bought on the first day of graduate school. I still have it. And I borrowed money from my TA because I had no money. But he was in the bookstore at U of Q. It's the weirdest thing. There's 60 some odd thousand students at U of T. Right? And I'm in the bookstore trying to, I get a calculator, and I don't have my wallet because I'm an idiot. And this is before there was Interac. You'd use these papery things called cash. And so I was like, what am I going to do? I didn't cry. I was a dog. I was a little concerned. And then this guy walks by, he said, "You're a new grad student, right?" In psych. I went, "Uh-huh." He said, "You need the what are you buying the calculator for?" I said, "Well, for stats class." He said, "I'm your TA. How much is the calculator?" I said, "It's like $20. I said, "Here's $20, just pay me back." He is now the chair of the psych department at Dartmouth College in the States. Todd Kennedy is his name. Thank you, Todd, for buying me my calculator, which I didn't pay him back for. He also helped me move once. He did, which was really nice. He had a pickup truck. It's from Calgary. They have to have pickup trucks out there. It's the law. It's kind of like here. It's a legal thing. It's in the Constitution. It's at the back. It's in the footnotes. You must have a calculator and a pickup truck and a snow machine. It's not nearly as funny as you're making this out to me. You guys are laughing at me, not with me, aren't you? You're making fun of me. It's Maria laughing. Okay. So maybe Maria, she's laughing at me, guys. You're not laughing.
No, it's funny because it's true.
Yeah. That's what I'm going for. That's what I'm going for. It's an observational humor. I'm a lot like Seinfeld. What's the deal on pickup trucks? So, this stuff is so dry and boring that I have to keep you interested by constantly doing bits. This is completely, by the way, me doing this on purpose. But seriously, this is pretty easy. Pluses and takeaways. I'm being sarcastic. Why? Do you have any questions on it? Because, I mean, you haven't done this in a while. Is it a good example? Yeah, it's a good example. It's an example that would... Apparently, this IQ improvement course works. Okay, great. There is a problem here. Problem one is there's no such thing as an IQ improvement course, but we typically don't know sigma for a population. I can usually come up with a value for a mean. That's easy. In fact, that's usually our question. Right? But standard deviation? And that's why the examples in intro stats textbooks are always about IQ, or they're about some industrial process. GE light bulbs have a blah, 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 and a standard deviation of 22.2 days of life. I don't know. They probably do know that kind of thing in those situations, but, you know, the kind of stuff we do, looking at human behavior, animal behavior, we don't know those things, except with IQ, which is a weird kind of variable. Well, wait a second. The expected value of S squared is sigma squared, isn't it? Right? It's an unbiased estimator of sigma squared. S squared is. Right. Well, that's a thing. We could probably use that. That seems like useful information. And it must be because I wouldn't just put stuff up here that was trying to mislead you. Well, except for that thing about the mean absolute deviation a couple of weeks ago. We could just sub S squared into for sigma squared. Into the Z formula. We could try that. Oh, but we now have two possible sampling distributions. We have one for the mean, and now we also have one for the variance. Because it's going to change every single time we take a sample. The variance will be a little bit different. It's got a sampling distribution too. And we were so close. So we can't just put it in and on its own we know that the sampling distribution of s squared, or s, doesn't make use either one, is going to depend on n minus 1, or on n, sorry. Because when we calculate this, right? When we calculate s squared, it equals sum of the x's minus x bar squared divided by n minus 1. And then if you want to take the square root of that to get the standard deviation, that's fine. It's going to depend on n. It's going to depend on n. So we have to somehow take that into account. We can't just use... The nice thing about Z table is we don't care about the number of subjects. Participants. I'm going to call them subjects. I don't know why people care about that. I really don't, but I care about being called subjects. Does anybody actually think it's bad to call people in an experiment? I know you're not supposed to, and I wouldn't do it. That's fine. If those people, I told you guys a story about the animals, and I said I'm not calling pigeons participants. But does anybody actually think it is? Because I mean, I'm old. Does it sound pejorative to call your people you're studying your subjects? Does it? Okay, maybe that's because we're psychologists too, and we've seen it written in papers so much. That's probably that's all it is. Maybe it really is mean. It makes them sound like, makes us all sound worse than Hitler. But I don't think it does. Yeah, there's real there's real problems in the world. That's sort of my view. But whatever. I'm sorry I went on that little editorial. We have to care about the number of humans or whatever. Peoples. So we can't just use Z, but we'll use something similar to Z. Something very similar to Z. We will use T. Discovered by a guy named Gossett, who went under the name Student, which is pretty cool because he wasn't allowed to publish, he wasn't supposed to publish under his own name. Wasn't supposed to publish under his own name. He worked for Guinness Brewery. Yeah. Charles, I think, Gossett. And they said you can't publish under your own name. They didn't mind their scientists, because breweries have a lot of scientists for them. They didn't mind them publishing. They just said, don't publish under your own name. We don't want some other company poaching you, basically. So just publish under a pseudonym. So he publishes this, calls himself Student, which is that's why it's called the Student's T distribution. But he's a statistician in a brewery. It's like my dream job. So what do we have here? Whoops, I go back. Sorry about that. So that's the T distribution. That's the sort of vanilla one, the regular one, the one that you've seen before for one sample t-test, right? X bar minus u divided by s over root n. We have, in essence, just taken something like the t-test and replaced the sigma with an s. Okay? That's what we've done there. That's what we've done there. So that's the logic of it. T, though, changes depending upon the number of observations, the n, because the sampling distribution of S depends on n. So it's going to change depending upon n. So what we call the critical value of T, the one we're trying to exceed define statistical significance, is going to change depending upon n. And as n gets bigger, T approaches Z, and they become indistinguishable. So the degrees of freedom to estimate sigma squared by calculating s squared, to be more precise, are what we actually care about. So we have, the question you ask yourself is, how many values did we fix to calculate s? And if you look at that, we fixed one of them. We have to know the mean to calculate x. That's one restriction we've put on it. So we have lost a degree of freedom. Okay? So we've lost the degree of freedom. So in this case, with the sort of one sample t-test, we have n minus 1 degrees of freedom. Little n minus 1. This is a pretty powerful technique because you actually don't have to know anything about the population. You have to know the shape of the distribution. You don't have to know the standard deviation. You have to know the mean, but you're always going to know that. Right? Because you're already asking a question, is this different from whatever, some theoretical value I have? So you're always going to know that. So that's actually pretty amazing. And the main thing is it actually works. I mean, this is the thing that is kind of striking about it. Questions? There's going to be, I think I have an example there too, so yeah, no worries there. All right. Questions? Again, I know you've seen this before, but don't feel bad about asking questions. For some of you, it was literally almost, for some of you, it could be as far as a couple of years ago, or at least a year ago. So don't feel bad about asking questions. Okay? You had second semester? Yeah? So you're okay. Of second year. And are you in first semester of third year? Or sorry, second semester of third year now? Yeah. So it's been a year for you. And that's probably... No, first semester. So it's like a year and a half for you. Yeah. Yeah. It's a while, right?
I don't remember if I had a first semester.
You were in class with us.
That's what I thought.
Okay.
We had first semester?
So y'all had a first.
Oh.
These guys take all their courses together. They get together and they plan. They also, it's too bad you're not two of you aren't wearing something identical because I can go with that, but you aren't. Okay.
What?
No, if two of you were wearing identical clothes of some sort, I would say that they also pick the same sweater, but you don't.
I'm wearing my work shirt.
What do you
It doesn't
wear?
work with me. Gym club.
Okay. There used to be two people in a class that always took the same classes together. These two young women who were in the class 8 years ago. They took all their classes together. And it was weird because one time one of them was in a class without the other one. And I said, so, where's Sarah? Here's Sarah. She goes, she's not in this class. I said, well, how are you going to go on? I will say the two of them made up a book of quotes of things I said and gave it to me on their last day here, which was really neat. And I didn't realize some of the things that I'd said, because then there'd be little references of what I said to them. Anyway, I'm not saying I want gifts from you, because I'd rather, like that, I like homemade. I don't want homemade crap. I like LCBO gift cards. Okay. Fine scotch, high-end gin. Just say it. I'm not saying you have to. And it would not help your market in the least. I can tell you that as well. But it would make me happy. And really, that's why you're here. I don't even know what I'm doing anymore. So, okay, let's say we had pairs of observations. So, before and after. Let's say we did the IQ thing. Instead of going 110 is 110 different than 100, we weren't very confident that we'd have a random sample. Let's see if they actually improved. So in that case, let's erase this. We had people who measured their IQ before and after, and we got 110 and 112, and 98 and 96, and 100 and 140. That's no good. That's ridiculous. 104. That's better. And we had 122 and 127. Okay. These are the same people. So now, what's our question? Our question is that difference, that's why it says x bar sub d, is this difference greater than 0? Right? So the difference here is going to be 2 and 96, 98, negative 2. And 4 and 5. Yeah. So let's see. 0, so 4, 5 is 9. 9 divided by 4, so it's 2.5.
Mm-hmm.
Is that right? Yeah. Okay. So now the difference is 2.5 plus 2.5. Is that greater than 0?
On the first one?
So you would say, wait a second, Dave, you have x bar sub d, but no minus mu, will mu 0? Because you always are interested in as a change from 0. Right? Because the null hypothesis is there's no difference. Right? Make sense? So if we were to calculate this, in this case, let's see if I can do this in my head. So we got 2.5 on the top, divided by S sub t divided by the root of n. Oh, n is 4, so square root is 2. Now I got to calculate, it's 2.5, so we got a half, and then we've got 5 squared, 4, quarter, 2.5, 4.5, 16, 4, 2.5 squares. It's going to be about, so 2 minus 2.5 is a half. And then we got negative 2 minus 2.5 is 4.5. And then we got 4 minus 2, that's 1.5. I'm just doing the deviations here. And that's going to be also 2.5. 2.5 squared, 2.5 is 5. No, 2.5 is 6.25. And 1.5, 15 squared, 25. 2.25, 16, 25. And 4.5 squared is going to be
He's just doing it.
roughly 18. I'm not going to do it all in my head, so it's going to be between 20, 27, about 30. Square root of that. 4. So it's about 3. It's 3-ish. Okay? It's 3-ish. You want to calculate it again? I'm just calculating. Remember what I said before, if you don't know the answer, let's pretend it's 3. 2.5 divided by 1.5. What did I get, 2.5?
No, just the 2.
What
Square
2?
root of 2.
Oh,
Yeah.
square root of 4.
Oh.
Yeah, that's all it is.
Oh.
Yeah. So then it's 2.5 divided by 3/2, which is 1.5. What do you get? A number less than 1. That's all we can care about here. It's so low. Yeah, man.
How do you get the SV?
Oh, I made up a number.
If we were.
Oh, if you were to do it, you were doing it's a standard deviation of all those numbers from the difference. Yeah, that's all it is. It's just standard deviation. That's all it is. Even though it's from differences, the numbers don't know where they come from. So you can calculate it. It's like calculating the mean of a bunch of means. The numbers don't know where they come from. It sounds weird. So the nice thing is here, we look that up and go, well, we already know. That's going to be a... So it's not going to be less. It's not going to be less than 1, but it's not going to be a whole lot greater than 1. And then we look up a critical value with n minus 1 degrees of freedom. N minus 1 is, in this case, 3. We look up the critical value with 3 degrees of freedom for t. Does that exceed it? I'm sure it doesn't. And we're done. And we say, no, it doesn't work. Ha-ha! Don't know why I did the ha-ha, the evil laugh, but I did. Whoa! Jumped right at me there. Let's put it over there. This could be used, that was for the same person, we use it for pairs of observations too. Right? We use it for pairs of observations. Sort of match pairs. So if we wanted to do something where, so we'd match on the variable. Let's say we have something we think, a drug that will reduce blood pressure. Maybe we want to match on blood pressure and have 2 groups in one group. So we have pairs and we find out, we don't care about anything else but blood pressure. We find out that I have exactly the same blood pressure as Sarah. So we are one pair. And you're giving the drug and I'm not giving the drug. And then you guys are another pair. We go like that. We're basically treating us like we're the same subject, you like you're the same subject. You can do that too. That's a pretty dangerous thing to do, statistically, because you're now throwing out any other possibility that any other variable matters. So blood pressure better be bloody important. Like I say, if your subjects are different, now they are different on everything except what we match on. You don't do that often. The idea of repeated measures you do, sure. Okay, questions? Okay. So So I'm not that far off. It's close to 3. Okay. What if your pairs aren't matched? What if you have 2 groups of subjects? Well, then you should just run for the hills. If I put more production value into the podcast right now in the background, you would hear Run to the Hills by Iron Maiden. But I'm not doing that. That's too much work. And a copyright violation. Maybe you have 2 populations. Well, that's the question you're asking. Are these 2 groups come from 2 separate populations, or they come from the same population? I was giggling to myself there because I thought about starting to sing Run to the Hills and decided to cancel. I have that album. It's vinyl, actual vinyl. I got a turntable, little USB turntable that converted to MP3s. It's pretty cool. Because I'm old. I'm old. I now know I'm old because my son asked me to buy music. I tell him he gets a song every week. But he also has a $50 iTunes balance from Christmas. He gets me to buy just shitty music. It's just... Sounds okay. He said, get the Green Day album. I can do that. I would have bought that anyway. And it's pretty good. But then there's a lot of other stuff that isn't good. It's demonstrably bad. Anyway. Our hypotheses are as follows. HO's mu1 equals mu2. Mu2, of course, my favorite band. Ha ha! I have a mu2 cup. I've been in my office. There's mu2 posters. I've seen them 6 or 7 times. It's the closest thing I have to a religion other than the Montreal Canadiens. So, and the other hypothesis, of course, is that mu1 is not equal to mu2. It could be we could go directional. Let's not. Let's just say we're going to be conservative and say they're just not the same. And when we say mu1 equals mu2, we're also saying, by extension, it's sigma squared sub 1 equals sigma squared sub 2. They're exactly the same population. Okay. I can't get Run to the Hills by Iron Maiden out of my head. All right. Questions? You've seen that before, right? Yeah. Okay. So the original T formula is this. We've seen it before. You'll see it again. You will love it. X bar minus mu over S divided by root n. Sure, you know that. It's a classic. There's our statistic that we're interested in. There's HO is here. And that's error. Okay? So the statistic is X bar. The HO parameter is mu. And the standard deviation, the error is this on the bottom is called the error. This is actually called the standard error of the mean. You'll see that used sometimes. I like to just think of it as I like the word error here. It's just a measure of sampling error. That's all that is. Great. So this is our old formula. Let's take this and substitute all the stuff about 2 groups into this. That's how we got this formula in the first place, from the Z formula. Let's try it like this. So x bar 1 minus x bar 2 minus mu sub 1 minus mu sub 2 over some estimate of error. Now practically that's this, x bar 1 minus x bar 2 over error, because practically mu 1 minus mu 2 should equal 0 if HO is true. Because they're the same. So it's the same thing with the repeated measures here, or matched paired t-test here. Double checking my calendar. Bugging me now with the actual standard deviations. Roughly in my head. I'm going to let it go. So practically it's this. Now we need an estimate of error. Variances have to be weighted because variances are dependent upon the number of subjects. They're dependent on the number of subjects. We have to weight them. We're going to divide them by their respective ends to standardize them. We're going to divide by their respective ends to standardize them. Okay? So now our formula looks like this. T equals x bar sub 2 minus x bar sub 1 all over the square root of s squared sub 1 divided by n1 plus s squared sub 2 divided by n sub 2. That whole quantity together, square root of that. So really, it's the same formula. It's actually exactly the same. It all comes from the same place. It really is the same. All we've done here is we've just subbed in again. It's the same way we got to the t in the first place. So we've got the value for the statistic, the value for HO, the parameter for HO, and the value for error. We subbed all those in. And we get this formula. Okay? Questions so far? If the variances are equal, and when I say equal, how much is not equal? Well, they're not going to be exactly equal ever. If they're exactly equal, something really weird's happened. But it's like, how unequal do they have to be? Well, there's a rule of thumb: if one's 4 times bigger than the other, that people usually use. They usually say, is it 4 times bigger than the other one? Then we'll change how we do this. So if one's 4 times bigger than the other one, or a lot of times you look at something and go, these two batches of numbers look different, but I didn't get a significant t-value. I wonder if it's a problem with the variances. So instead what we do is we calculate something called a pooled variance. It's a pooled variance. S squared sub p equals n1 minus 1 times s squared sub 1, and then this plus n2 minus 1 times s squared sub 2, divided by n2 plus n1 minus 2, because we've lost 2 degrees of freedom. We have lost 2 degrees of freedom because we have estimated 2 means. We put 2 means in there, right? So we lost 2 degrees of freedom, not just 1. The rest of this stays the same. We just do it here, okay? The rest of the t formula stays the same. So how many degrees of freedom? This many, n1 plus n2 minus 2. Because we've estimated 2 quantities, x bar 1 and x bar 2. So all you care about now, you do the calculation, what the heck it is, and you divide by, so that you look up what the critical value is for whatever degrees of freedom are, and you see, is our t obtained, is it greater than our t critical? And if it is, we say it's statistically significant, and we go from there. So the question always is it statistically significant? Is t obtained greater than t critical? And as convention, by the way, I said, what if you get a negative number for your t? Always put the biggest number as your first mean. That's just the way to do it. Then you'll never have to worry about it being negative. Because then if it's negative, you can say, is the critical t value, and I put the absolute value of it, that's it. Just make the biggest one first. Put the biggest one first. The interesting thing is, this is actually an approximation. This was done. There's a better way to do this that I'm not going to show you how to do by hand because it's horrible to do by hand. But there's a way to do this with what are called partial degrees of freedom. And if you did this with SPSS, and all you have there, pull it up in SPSS, you create two variables, and then there's under Analyze, you do compare means, and it'll give you this one. It'll give you one with pooled variance. It'll say that. It'll say equal variances or unequal variances, I think is what it says, or it says unequal or equal variances and pooled variances. It says one or the other. I can't remember. This one with the pooled variance is unequal variance, or it'll say pooled. But then it'll say something with partial degrees of freedom. It'll have like 11.3 degrees of freedom. That's actually a better way to do it. But doing it by hand, this is so close to being the same that it doesn't matter for all practical purposes. But the partial degrees of freedom one's probably better. It involves doing matrix algebra. Who here's done matrix algebra? Yeah, me too. That's it. It's horrible and it's evil, and you don't forget it. No one does those by hand. No one does these by hand, frankly. Really, t-tests. I shouldn't say that. But typically you don't. Typically your data's already in a spreadsheet. Why not? You can do this, by the way, with Excel as well, or Google Docs does it, like Google Drive. So there are online tools out there that'll do it too. Okay, so if you do next year, let's say when you're doing your thesis, or this year when you're doing your thesis, how many groups do you have, Sam? How many groups do you have? Oh, just two? So you probably might be doing a t-test. Do you think so? Yeah? Well, if you are, you might want to look, if you talk to your advisor about this, don't just listen to me, but you might want to look at the partial degrees of freedom and just see what it says. If it's the same as this, just use the one with the full ones because people understand that better. Always, and that's what you almost always see in the literature. You never see partial degrees of freedom, but the reason is no one's taught it. And it's always so close. The partial degrees of freedom answer is actually a more accurate answer. But we're using this, we are interested in statistics for fun. We're using these tools simply to get somewhere. We're using them as tools, not as an end in and of themselves. Okay. There are some assumptions. You have a simple random sample. A simple random sample is just literally where you have a sampling frame that has every possible subject on it, and you randomly select subjects, or as they say in statistics, experimental units, from the population. No restrictions. Does that ever happen? No. Does it matter? Nope. Not really. You can violate the hell out of that assumption. It's great. You can really violate it. The t-test is really resistant to violations of this assumption. It's great. Independence of observations. You can't violate this. The math that's behind this makes an assumption. Now, those of you guys that have done a little bit of even advanced math in high school know that a lot of times when you're doing like an identity or something like that, or any algebra, the problem will say, assume the following. Well, this is one of the assumptions. One of the assumptions is each observation is independent. So if I know one score, I don't know anything else about another score other than that it's a score. Okay? So if I know Bree's number, like her score on something, I don't know Maria's number. They're independent of each other. You can't violate that. You violate that, and in fact, it all falls. And you might think, why does the math fall apart? Because it's an assumption of all the deeper math that's behind this. The nice thing is we can usually deal with that pretty easily with design. That's easy to deal with design. So that's fixable. Okay, so that's a design question. That's not really, while it matters to the statistics, it is really a design question. There are statistical techniques that can use dependent observations. They aren't this. And finally, you need homogeneity of variance, meaning the variances of the different groups are the same. Now, they're never exactly the same. But this is a null hypothesis assumption. Because the null hypothesis says the groups are equal and the variances are equal. If the means are equal, the variances are equal. Okay. So the stuff you're calculating, these S squareds have to be pretty much the same. You can violate this not as badly as you can violate simple random sample. I've seen statistical papers. Yes, that's right. I've read statistical journals. It's really fun. Where they play around with this and they violate simple random sample to the point of using making everything gone. It's beautiful, and it still doesn't really affect anything. But when you violate this, and roughly around, you can violate to a point, but around 4 to 1. That's when you say, well, one of them is 4 times different than the other way. As a rule of thumb, you say, okay, I can pull the variance, or I can look at that partial degree of freedom technique that comes on a computer, or I could use some other technique other than a t-test. Or finally, what about changing the numbers? And you say, wait, you can't just subtract 3 from all of them or something. No, nothing like that. But you can transform your numbers. You can make it a scale problem. And remember the first homework assignment, you had a transformation on there, right? You turned inches into centimeters, or centimeters into inches. That's a transformation. They're both measuring exactly the same thing. Height in centimeters and height in inches are perfectly correlated. But you multiplied by a number and it changed the variance, didn't it? It has to, the numbers changed. But typically we can deal with this. You're not going to have 2 groups that have 4 times different variance. What you're typically going to have when you do this with some stat software is it'll come out and you'll get your 3 answers for variances equal, variances pooled, and partial degrees of freedom, and all 3 of them will have the same, almost exactly the same t-value, and all 3 of them will have will agree on the significance or not. That's just the way it works. Okay, does anybody have any questions about this stuff today? I know it's a lot, and I know it's been a while for some of you to play with t-tests, and that's fine. All right? Thank you, everybody.